Well, a very warm welcome to this GAN 2025, a short course on supramolecular crystallography and soft orthometrics. We are thrilled here to have you join us for this exciting learning experiences. My name is Nidhi Kumari. I am a senior research fellow working with Professor Swamiji Roy. Today, I am here to host you for this 5-day intense course on the behalf of organizing department and as a Kolkata. I welcome you all here. I extend my hearty welcome to all participants, our esteemed faculty and distinguished guests. Young, as you know, is a prestigious initiative by Government of India aimed at leveraging the expertise of leading international faculty to enrich our academic ecosystem. This course is a testament to that vision, bringing together renowned experts and passionate learners. With this, I would like to call the Dean of Administration, Active Director, Professor Mohit Prasad on stage to say a few words. Have a huge round of applause.
Thank you, Nidhi, and good morning to all. And I welcome all the participants to this GAN program. I believe that this is a program which is going to be very useful for all the participants who have come from this part of the country. I believe people are from bachelor's, master's, PhD, so it's a wide spectrum of people here. And this GAN program is on supramolecular crystallography and soft oxalometallics, and it's being coordinated by Swamiji from the Department of Chemical Sciences. So the main resource person is Professor Kari Ishanan. I welcome you, Professor Resanan, to this part of the world. I was just briefly chatting and what I realized that he has visited India a couple of times, 7 times altogether. So he's not new to India. So he has been to Hyderabad, Bangalore, Delhi. So I could get all the names from him. And I believe that this is the first time he's coming to the eastern part of India. And this is a very green campus. And welcome to this part. He's an expert, leading expert in the area of supramolecular crystallography, and he's the head of the organic department in the University of Jyväskylä, in University of from the country Finland. And I believe Finland is a very beautiful country with a lot of sea around. And so welcome to this part, and I welcome all the participants, and there will be other speakers also from ISER Kolkata, where we have BCS chair, Devashish, Shamaji, Rahul, and you have people from Jadavpur University and University of Hyderabad. So I welcome all the members here, and I believe that you will, I wish that you will have a very good time. You will learn the basics of this, what is the basics of this topic, which is the supramolecular crystallography and soft oxalometallics, and what are the applications associated with it. Okay, so this is an important bit, and the 5 days, what Nidhi told will be quite intense. Okay, but you will have some rest time in between Saturday, Sunday, so you will get some time to wander. I welcome you to visit the labs here in the various, we have 5 departments here, 6 departments. So whenever you get a time, do visit the labs around and you get a feel of what people are doing. So it's always good to know what's happening in this part of the country. Okay. With that, I would like to stop and thank all the members, including the speakers who have come here to this part of the country for attending this program. Thank you so much.
Thank you, Professor Prashad. Now, we would like to call on stage the head of the department, Devashish Haldar, Professor Devashish Haldar, to say a few words.
Thank you, Nidhi, and very good morning and welcome to this grand program. I sincerely thank Shomoli for organizing this and also Professor Gary to agree to come in this part. And so, on behalf of Department of Chemical Sciences and once again, very good welcome. So this program is scheduled for 5 days lectures. So there will be lectures as Professor Mohit already said. From Professor Giri, Shomo, myself, my colleague Rahul, and then there will be lectures from Jadavpur University and Hyderabad University. So I hope we will enrich by this grand program. And about Department of Chemical Sciences, this is mainly for the students who are coming from other institutes. And Department of Chemical Sciences is one of the leading chemistry department of the country. Though we are only 17 years old and we are doing well. So at present we have 35 faculty members, including 7 theory and computational chemists in the department. We serve almost all the discipline of the chemistry, all the area, and we are publishing very well. In fact, we are publishing in all the leading chemistry journals from almost all chemical society are publishing from. And so, with this note, once again, thanks for coming. Enjoy the lectures and learn. Thank you very much.
Thank you, Professor Haldar. So, I would like to call upon on stage the foreign faculty expert, Professor Kari Resanen from University of Uppsala, to say a few words about this case.
I think I have to speak to the microphone. Do I? You can hear me anyway, but I think if this goes to the online, I think it's needed. I made a joke yesterday in the college in Kolkata that my wife always says that I don't need the microphone, I need the silencer. Lecturing will be, of course, easier in that sense that you can hear me. But that's the idea. So I'm very happy to be here. And as I understand now, we don't start yet. Just a couple of words about the course. I've really been in India 7 times, so it's always a pleasure to be here. And this is my 2nd time of giving lectures. This is the biggest lecture tour I've given outside Finland. And the course, what I will be doing now in the 5 days, will be part of, or it's partly what I'm teaching in our university. So this is for undergraduate and graduate students. And it doesn't cover any mathematics, so it will be easy for you to follow. It's also very practical. And if you have any questions or anything of this kind, because my idea is really teach you to understand the crystallographic thinking, and then it will be then supported by the chemistry of the soft materials in that sense to cover these things. But that's really everything I want to show you now. I'll talk to you now. I think someone will say a few words and then we will start. And then when we start the engines, then we go. So I think it's your turn now.
Okay, so very good morning. I welcome you all on behalf of IISER Kolkata and also the Gyan program to this program. Now I will say a few words also about Professor Kari Resanen, who is the key person of this presentation. Now for this course, I would also like to say you a few words about this course. So the idea is to bridge the gap between the basic knowledge and advanced expertise knowledge. So it is to give you a hands-on feel, as Professor Mohit Prasad and Professor Devashish Haldar already mentioned, that you will have the level of basic understanding and you will go to levels of problem solving, and there will be also an innovation workshop at the end. So the idea is that you develop the basics so that when you join a lab for research, or those of you who are doing research, who are interested in crystallography, can have the idea that what it means to do crystallography and to do soft oximeters. Now crystallography, as we were talking yesterday with Professor Kari Risanen yesterday, that nowadays it's very easy because you can just have a computer and you just have the program that is always prompting you, and you click buttons and you get a structure. But that is not crystallography. So you have to apply your basic mind to what the structure that the molecules might have or will be having. And you will tackle these problems with hand-on exercises from Professor Kari Risanen. And then how it is applied, because crystallography is applied everywhere, especially in the pharmaceutical industry, that you know that there are different polymorphic systems, there are different types of handedness, which can be from a benign molecule, a pharmaceutical agent, to a toxic agent. So that's where you need crystallography, and it's now everywhere, even in the PCM materials, that means phase change materials, you have crystallography. You have crystallography everywhere, even in protein crystallography and so on and so forth. So this will have, and with soft oximeters, that's the border. So these are the soft matter which are not crystalline, and we will look at the structures, we will look at the applications, for example, how the things change. And with Devashish Haldar, we'll be talking about, Professor Devashish Haldar will be talking about soft matter systems and supramolecular gels. Rahul Banerjee, Professor Rahul Banerjee will be talking about MOF and COF type systems, which also uses crystallography. Then Professor Shamod Dash will be talking about crystallography in polyoxometalates, and then Professor Dipojyoti Ghoshal will be talking about critical problems, charge density problems in crystallography and things like that. So you will have a bouquet, but it will be an intensive course, and we encourage you to please be on time and please start. So because this is also being webcast, and I also thank the Gyan authorities for granting this grant so that we could host the faculty, and of course ISER Kolkata and my group also who have been working tirelessly. Now with this, because we will conclude, so I will just give a quick introduction about Professor Kari Risanen. So Professor Kari Risanen has over 30 years of research experience, which matured to a world-known expert on X-ray crystallography of supramolecular structures, weak intermolecular interactions, and especially halogen bonding. And he has been the part which has of IUPAC which has defined halogen bonding. So he is a world expert of halogen bonding with more than 850 or 900 papers, and with extensive expertise on other systems as well. And he got nominated twice as the academic professor, the highest ranking academic professor available in Finland, equivalent to the European Research Council Advanced Grant. And he has also been awarded the prestigious Humboldt Research Award in 2017 and appointed as the Doctor Honoris Causa from Tallinn Technical University, Estonia. Within the Finland's honor system, he has been awarded twice Commander of the Order of the Lion of Finland, which is the highest order, in 2016, and the Knight, first class, of the Order of White Rose of Finland in 2008. So you have the privilege of interacting with one of the top minds alive and among us in this field of crystallography. So it's a great privilege, and I thank Kari for being there, and he has supervised more than 50 postdocs, 38 PhD students, and more than 170 master students. And he has a massive H index of around 77, 84, 2025. So it's a real pleasure and privilege, and I encourage you, as Professor Prasad said, to explore the opportunities also in ISER, because you are from everywhere, to go and visit the labs, knock on the labs, have a look, and also take this advantage to interact with Professor Kari and us as much as you can. So with this, I thank you for joining us here today, and I hope that you will enjoy this program and it will be a fascinating journey as we also expect it to be. Thank you very much.
Now, to express our sincere appreciation to our esteemed guest, Professor Kari Lisanen, I would like to invite the respected HOD of the department, Professor Devashish Haldar, and the Dean of Administration and Acting Director, Professor Mohit Prasad, on stage for performing the felicitation. Now I would like to now Professor
The amplifiers, because then you make it even more, so you don't get scared. Sometimes there's that, then, no, but it's nice to be here. But right now, really, how to start, I would use a couple of words to tell you where I come from. Of course, it was mentioned already, but it might be nice for you to see where I come from. And then, actually, this is only 3 slides, maybe 15 minutes, and then I will start the real teaching of the real course. And this is more like information now, what we have here. Okay, I don't have a pointer, but where I have it, there's it. Okay, it works. Right? Yes, it works. Great. So the point really that I'm coming from Finland. Finland is here. It's really in the Nordic countries. So this is Africa, of course. This is Russia, big Russia, then China, India, here, Australia. For some reason, I kicked out the United States because Trump is there, but anyway. But of course, this is not in real scale. So India looks very small, but actually it's not a small country. Also China. But Finland is quite a big country. So I'm here in a really bigger sphere. I'm really close to the Arctic Circle and North Pole. And the point is, our capital is called Helsinki. I'm not from Helsinki. I'm a little bit further north from Helsinki, but I will show you in the next slide where I come from. But that's the idea. I have a direct flight to Delhi. And before we were able to use the Russian airspace, so more or less direct flight here for 6 hours. But now, based on the reasons, the Russian airspace is closed, so we have to go through here. And it's 8.5 hours. So the flight is 8 to 9 hours in there. And the distance is there. But the point is that where are we? So if you look for geographically where we are, where Finland is, we are between 60 and 70. And the Arctic Circle is 66. So 1/3 of Finland is actually above the Arctic Circle. So we are an Arctic country. So we have really temperatures way below 0. We discussed yesterday and the day before that the maximum difference between the maximum and the minimum temperature in Finland has been 72 degrees. So in winter it was -37. And in summer it was +35. So we can have this 30-degree temperatures nowadays during the summertime, but that comes mainly from the global warming. So the global warming has a big impact here when you are close to the poles. In here, where you are, you see that the storms are more heavier and more stronger. But that's the idea. So India is between 8 to 37 roughly. The idea is, and Finland, if you look for the size of Finland, so it's 338,000 square kilometers. So it's quite big. I think we are the 5th biggest. So this is of course lying, for example, France is bigger than Finland. Sweden is slightly bigger than Finland, Norway is not. So these are roughly on the same scale, but Germany and France are big countries also, and India of course. But the point is the population, we discussed about the Kolkata. Kolkata has roughly 20 million or so. So Finland is 1/4 of one big city here in India. In India you have now 1.4 billion, so 1,400 million persons. And so Finland is like a very tiny, okay, let's call it a very tiny city, or not a village, but anyway, here in India. So we are very few persons in a big country. Which means that we have, on average, 16.5 persons per square kilometer. I mean, here, you have to be really on the countryside in order to reach this. And you might not even reach this low number. So in your case, it will be 10, 100 times, maybe 100 times more than 100, 150 persons, or 50 times more persons than we have. So the point is that then our aim was, of course, to go from Delhi to Kolkata, and that was a short flight, 2-hour flight. So this was 2 hours, 1.5 hours, and this was this 8-hour flight. So that's the idea. So it's a long distance, about 6,500 kilometers in geographically, but of course with the local flights you can easily do it. But this is now the map of Finland. So this is actually the country. Now it's so it's 1,500 kilometers long. And this part here is a border to Russia. So we have the longest European border to Russia. It's 1,300 kilometers long, or even longer. And the point in there is that Finland is a long country, rather, you can be narrow in that sense. And the place where I come from is here. And now, surprisingly, this part of Finland is called Central Finland, although it's in the south. But if you look carefully, you can see the lower part of Finland and then the upper part of Finland. The upper part is Lapland, and that's why this part here is considered to be Central Finland. Although the whole country is called Finland, but former times, everything happened here. There's virtually nothing but reindeers in this Lapland area. But that's the idea. And this yellow point here is the Helsinki, the capital, where I started my flight. So I drove a car, 3 hours by car, 300 kilometers. And then the blue ones, what you see here, are lakes. So we have 188,000 lakes. So we have a lot of lakes. And we eat fish and all these kind of things, what you can easily imagine is happening. Also, we have a lot of wild animals in the forests. But then one of the important things that I already discussed yesterday, look here. There is a Christmas tree. And the reason is why there's a Christmas tree here is that the Americans stole Santa Claus. And then they tell that the Santa Claus lives in the North Pole and then flies with the reindeer. This is not true, because the real Santa Claus is living in here. Everybody knows. And he is not flying, he just had a sledge with the reindeer. So he's not flying. We are more realistic. And the point is, there's a mountain, a small mountain. We don't have big hills, there are a mountain, and it has a specific name. Everybody in Finland knows that the Santa Claus is living in this specific mountain, and the mountain is called Ear Mountain. So the ear like this. And it's a real one, so it's in Finnish the same thing, so it means ear. But the point in there is that maybe there is a reason that it's considered that that's Ear Mountain, because the Santa Claus is listening what is happening there, and then starts the journey in Christmas time. So that's the idea. But that's the part of the joke. But the point is that this is a typical picture of Finland. You can see in May, about one of the lakes here. We have a lot of islands there, and then there's the boat. Somebody's going to fishing. And this is a very typical thing what we have. The other extreme now, look, this is done more or less, I think it's around 11 o'clock in the evening. Because we are so far north that we have extremes with the sunlight. So in summer, there is no night. And in winter, there is no day. So if you go high enough, somewhere here in this region, the sun will go down and stay down for 3 months. It's not pitch black, but the sun, you can't see the sun. And then in winter, you can have something like this. So this is a forest with a lot of snow, frozen ice, of course, or water. And you can see this tree is very particular here because you can see it curves. So there is so much snow in the tree that it might crack the tree. This can happen. And this is the other. And then you can't see it very nicely, but there is a skiing track here, not skating, skiing track here. So we are doing a lot of winter sports, of course. Ice hockey and skiing, this, because we have a lot of ice and snow. But now the global warming is really changing this thing a lot. And now, when I left in Helsinki, it was +8 degrees. I started on Tuesday, which is completely abnormal. Normally we have -5. So we see temperature raise about 10 degrees now in the winter time. And in the summertime, we might easily go over above 30. Because what we have here, Russia is a big continental area, so we can have a lot of continental air coming. But these are quite popular for Finland, but I think we might have also heard, and if you have a connection to YouTube, go and Google Northern Lights in Finland. Then you see something like this. And you can have this in Lapland. The more north you go, the better you can see this. But these are really rare. So I told my colleagues, they said, you see Northern Lights every day. I said, no, I've seen 4 times in my life. And in 65 years, I've seen this 4 times. Because they are hiding. They are there at night, at midnight, 2 o'clock in the morning, and so on. It has to be clear skies, because they are, of course, beyond the clouds. If there's clouds, then you don't see anything. But this picture is taken by Rosie. Rosie is, surprisingly, by the way, an Indian postdoc in our department. And she took the picture at midnight, and why this is important, this shiny, little bit shiny area is difficult for you to see. It's a lake. And this is a boat. And this is the Department of Chemistry. So our chemistry department is beside the lake, so you can come to the chemistry department by boat. Theoretically, you could come from here. It will take years, but in theory it's possible. But the point is, this is a typical color of the Northern Lights. We call it also Aurora Borealis. That's a Latin name for this, and it's green color. And the point in there is that these are actually changing. It's not like a static image. They are changing. They're moving around. And this year has been extraordinarily good for these things. I haven't seen them myself, but there's a lot of movies, videos about these moving Northern Lights in the YouTube. Just go to YouTube, and then Northern Lights in Finland, you will see a very spectacular thing, because they show all the colors. Not only green. Green is a typical one, but all the colors you can see, from white to purple and blue eyes and all these things. So that's the idea. That after this lecturing and all this kind of, when we have a break, so you can ask me questions about also Finland if you are interested. But that's the, in a sense, the introduction where I come from, and now we start the real engines. So the idea now really is to go through and teach you a basic theory, basic facts, not mathematically, but on a conceptual sense about single crystal X-ray diffraction, what it means, what we can do with this. And I will have also a walkthrough here in this course. And I can provide you programs, and I can give you a link to the programs, what I use here in this course. And I can give you the data, I can give you the material for you to work by yourself if you like. If you are more experienced person, and have done some of your work, and you have problems with this, you can ask me. So I can tutor you, and help you on complicated things. But of course, in this course, we cannot go deeply on the complicated things. Remember, this course is for teaching somebody who has never done anything. just really start from the basics and try to teach you what is there. You might have gone some courses yourself, but the point is, don't worry about this, because I will then cover these certain things from a different perspective. So, because the theory of X-ray diffraction is solid-state physics, and you can describe that purely mathematically, but then you lose the real idea, because as someone was saying, the idea that you can use computer programs, and computer programs are doing a lot of work for you. But the point, that's also the pitfall, because if it's too automatic, you might trust what the computer program is telling you, and this is not correct. Sometimes you have to be able to see that now the computer program is not able to see the real thing. And I will show you some of the pitfalls, which is a very typical thing, and I emphasize it many times, that the X-rays don't see the atoms. So X-rays don't know anything what is there. The only thing what they see is so-called electron density, and this is what you'll learn later on. And you have to, when you are doing your work, you have to tell these programs what are the atoms. And this is a big thing. This is sometimes you might make a mistake if you don't know. So doing a completely unknown structure by X-ray diffraction can be very complicated. Because the idea is that the X-rays don't see, for example, difference between a carbon and nitrogen. They look the same. And then it's up to you to think about, okay, now there are 4 bonds from this atom, and it's not charged, so it cannot be a nitrogen. It has to be a carbon. Because if it would be a nitrogen and you have 4 bonds going there, it should be a cationic, and then you should have an anion. So there is a lot of chemical information you have to know in principle in order to understand what you see in X-ray diffraction. And this is just the idea of these kind of things. And the first talk, the first hour, is just introduction to the history of X-ray diffraction. When it was developed, who did it, what was the discoveries, and so on. And this is just this. So the point in there is that this is actually a nice summary slide also, in that sense, because you can see pictures of crystals. You will learn how to look into crystals, not with the microscope now here, but theoretically. And then also learning about how to make the crystal, how to crystallize. This is a very important thing, because the X-ray diffraction is a very unique technique in a 2 ways, in a plus and minus. So the point in there is, when you manage to grow a single crystal, I will then teach you what is a single crystal. You manage to do a single crystal, then with a very high probability you will get the atomic resolution. You can locate all the atoms. But if you don't, you don't get anything. So if you are doing a mass spectrometry or NMR or any other analytics, you can run the experiment. But you cannot run the X-ray instrument. It's always a measurement, and only after the measurement, if it's good enough, you can have the result. And that's the reason we cannot ever promise in advance that we can get it done. So we have to do the work, and only after the work is done, we will see that, okay, what was the result? Is it what we expected, or is it something different? So we have to analyze. And this is also what I am teaching here in this course, not only to do the work, actual work, but only analyze, look what you can get out of it. And it's a learning process. Nobody will be an expert after one course. When you have done 50 or 100 structures by yourself, then you start getting an idea, okay, what is going on. And that's the idea. So it's really a learning process. There's a lot of handwork what you have to do. But there are. So single crystal, diffraction pattern. This is what you see in the modern instruments nowadays. There is a MOF structure, of course. We can study any kind of structures. So now the course, or the title in principle says supramolecular crystallography. What it means actually means that we can apply crystallography to supramolecular structures. But the crystallography is always the same. It doesn't matter if it's a POF, MOF, or pharmaceutical, whatever, it doesn't count. So that is not the issue. The issue is single crystal.
Once we get the single crystal down, then we can do these things. And then here are instrument pictures, there's a powder diffractometer, and different kinds of things. These are all things what you might see when you're doing the work. And then this clearly doesn't lock a single crystal out. And then what you have to do is try to figure it out, can I have single crystals out of this? Because if you can, then you might be able to get the structure. So because this handout, this is also available for you as a PDF. I will provide them to him. And there is some information about background materials. You don't have to go through this, but this is just information for you. There is a lot of these things with the simple books from Professor Clay, and then a more complicated fundamentals of crystallography, which is here, which is really a heavy book. But you can see they are all 20-year-old roughly, so because the theory has been developed 100 years ago. And there is a list of these things, different kinds of things, the crystal structure analysis and so on. You can see this book, for example, is a very nice book, and it's from 72 and still absolutely valid. So the basic theory has not changed. So the way how we work have changed because the computers have developed. And that's the idea. So I will not go in details in here. But then you can also go, there are some websites. And this is a collection, quite old collection. I think this is a 6 or 7 year old collection. But some of these things work. So you can go and click any of those and they will take you to the surprising. Let's put it up. That you can go and see different things in the web. And there's a lot. Even if you go to Google and say X-ray crystallography, you will get a nice page on that. So the information is there. But the information doesn't help you if you don't understand what you're doing. This is actually what we are doing here. So I will list also the programs I will show you and use in this course. These are freely available programs for scientific use. I call them Mercury. And then the Mercury is a freestanding program, but it's also associated with chemistructural database, because this is also a very important tool for us. On any kind of a thing, MOF, GOF, or colloidal whatever, all these are stored, the X-ray structures are stored in the chemistry-crystallography database. And it has now down here, and now this is a little bit older, there is 1.4 million X-ray structures now. And we also go through in this course how we can look into the chemistry-crystal database and how we can study the structures there. There is a homework which is associated with this course in my university where the students have to do the search and see if the structure is known or not. And then OLEX2 is also a program set which is also freely available. We use these things. And don't worry about this. You don't have to worry about this. If you are interested on this, use these programs yourself, then I will then provide you. I have a link for this program. It's a Dropbox folder, so it's available in there. And then the ShellX programs are the same. You might have heard ShellX programs, and this is a different set of programs which works inside OLEX2. So I like this OLEX2 program set because it's a very visual, it's easy to and I will have a walkthrough of the X-ray structure solution using these programs. But now really about the X-ray. So this is really a discovery what was done about 150 years ago by a German researcher. Actually, I think he was a doctor, Wilhelm Röntgen. And the point there is that we have to go through a bit of the history where we come from. Because the X-rays were not actually designed or discovered for that use from the beginning. So the idea is that he got a Nobel Prize in 1901 after the discovery of the extraordinary services returning with the discovery of remarkable rays subsequently named after him. Because when he realized that these rays would pass through material. And the point in there, what has happening is that you can create an image of a material based on this, depending on how dense it is. And this is actually the hand of Wilhelm Röntgen's wife. And this is the original image. You can see the idea is quite okay. You can see the bones. You don't see the muscles because they are penetrated by the X-rays. And then the ring. Actually, she has a ring here, so that is the ring. And now this is a higher resolution X-ray image of her hand. And you can see the idea that how the joints are there visible. So now you can easily understand that now you can look inside the person. And when you're looking inside the person, you can see if everything is okay or not. So this is, of course, used to look for bones. If you have a broken hand or bone, it's visible in X-rays. But that's the idea. This is the idea. But we don't, of course, use X-rays in this way. So the next person who is associated with this thing is Albert Einstein about the quantum theory of light, because now X-rays is a part of light. And now we have to know the behavior of the X-rays, meaning light, and how it behaves, how it interacts with the matter. And that's the idea of that we consider of photons were associated. And the point is that photons are tiny packets of energy which has a characteristic both particle and wave. So now our work is better understood. We consider the light as wave, because all what we do this, we describe this as a wave. This is the easier. We speak about wavelength. And that's an important issue in our case. And that's the idea. So he then coined, of course, the famous E mc squared based on that. But that's the idea. So we disregard the particle nature of the way we look at as a wave, or light. We look at as a wave. And that's the idea. He got the Nobel Prize in 21 on this theory. The first is the discovery of law of photoelectronic effect. So that's part of the phenomenon of light. But what is important in the wave, or light in general, is a wavelength and amplitude. And these are the important points, what we need to know. We don't have to really understand the basic physics in here. For our purposes, the wavelength and the intensity, the amplitude, is important. There is one feature which exists with the light, which is the most complicated thing for us. It is the phase of the light. But I will come to that later on, because without the information about phase, so where the maxima and minima are, is important. But then, in 1912, Max von Laue and Friedrich and Ipping, they did an experiment of continuous X-rays, all wavelength, through a crystal of copper, sulfate, and zinc, and realized now something is happening. So they didn't now make an image of it. They realized that X-rays will diffract. So they bounce from this crystal. Something inside the crystal is bouncing the X-rays, and that is the thing what they discovered. And this is what happened. So this is the first diffraction image. Diffraction meaning now it's the same as wave or light is bouncing from mirror. So that's we can call it diffraction. Then it's because diffraction is in principle the same as reflection, but diffraction is because it will have to interact with the material in order to do this diffraction. And later you will learn where this diffraction comes from. But that's the idea. And then the idea of crystals are decomposed periodic atoms and cause distinct X-ray diffraction patterns due to the atoms and their three-dimensional spacing. This is now the first really important information. So now, if you read this reversed, it means that if we know these points, we know this point's position and we know the intensity, we can, in principle, follow back to the crystal on that point where the diffraction happens. So we can actually follow the light reversed on the spot, on the position where the diffraction happened. And this is actually what we are doing. There's a lot of complications how to do this. It's not a very simple thing to do, but luckily the theory of this has been developed already more than 100 years ago, so we don't have to worry about this. But this is the idea. So they received a Nobel Prize in 2014 on the discovery of diffraction of X-rays by crystals. But now there is no real structure. There is really information that now there has to be a periodical order of things. And that's the idea. So then, really, 1 year later, or 1913, there was their father and son, Bragg, who actually were building up an instrument. The instrument is here now. What they did, they shined light on a crystal and then used a detector here to do it. So this was really like, or looks a little bit like our diffractometer, but now it was not monochromatic, so the continuous X-rays. And now these guys, both guys, were studying the phenomena, what is happening, and they found out that there is a law. There is a certain regularity which is filled up by a very simple law. And this law was then later named as Bragg's law. And the Bragg's law is a very simple thing to do. But there is a lot of things in there. So now consider these points. For you it's easy to, let's say, understand these points as an atom. So let's consider that the blue is an atom. And now when you look for this atom, take any atom here, when you see its neighbors, they are always the same distance away from this point. So in this kind of a thing, we have a periodic system where we can think about that there is a one layer of these atoms here, and the second layer in here, third, and so on. And now when the X-rays are going and hitting in here, they will hit the electrons of the atoms. We will see that later on. So it is, and they bounce off, diffract from here, and they diffract following this law. So now, the wavelength, the multiplicity of the wavelength, normally n, we always consider n as 1, so it means that the wavelength is proportional to the distance, double the distance of these points where the bouncing is happening with the angle where the diffraction is happening. So why this is important is that when we know the lambda, the wavelength, this becomes constant. We know we can measure the angle. So with the instrument we can measure the angle. Then this becomes known. The only thing which is unknown now is the d, and we can easily calculate. So this now, this law actually tells us a lot of information from which kind of order the diffraction is coming from. And this is the essence of all diffraction. And we have to follow, we have to try to figure it out how we can use this in our measurement. And this is really the idea. And now the Braggs actually got the Nobel Prize for the next one. That they showed that they can use this diffraction pattern to determine relative positions of atoms. Because I go back, so the point in here, there is no real, that's the Bragg's law, that there is no real structure, it's just they're ordered. But now consider that you have real atoms, or real molecules in there. If they are ordered in the same way, and they can diffract X-rays, you can actually then determine the structure. And this is what they did. So they showed that diffraction pattern can be determined, the relative positions of atoms, within a single crystal. So I will always emphasize single crystal. And the single crystal means two things. It has to be a single entity which is perfectly ordered. Because if it's not, then you will not get a unified or clear diffraction pattern. And then the Bragg's law doesn't apply. So in order that the Bragg's law is applied, you need to have a periodical ordered structure in 3 dimensions without errors and anything like this. And this is the most complicated thing to do, to get the single crystal. As I told you in the beginning, if we crystallize any material in a nice single crystal, it's very likely that we can get the structure solved and then see what we have. But if there is an even tiny errors in there, then the mathematics don't work anymore, and then there is no help. You cannot make something happen if it's not there. That's the idea. It's like multiplying 0 with any number is 0. It's the same thing. But that is the idea. So they got the Nobel Prize in 1915 with the services of analysis of crystal structure by the means of X-rays. So this was actually the starting point, and now it's 120 years ago. and everything done. So we are dealing with a very old thing. But it's interesting that with this very old thing, we can measure and do research on a brand new, unknown systems. So then in 16, they developed a different technique. It's called powder diffraction. In this course, I will not consider powder diffraction. It's a special case of a single crystal, but there are a couple of slides showing this, but I will not really go in detail. But the point difference in here is that you will not anymore get a single diffraction pattern as you saw previously. You get, because there is a mixture of different crystals, you will get lines. You get a diffraction pattern, but the diffraction pattern doesn't look the same as from the single crystal. But it's very handy and it's very practical. And these guys, Debye and Serre, Debye got the Nobel Prize and contribution for knowledge, molecular structure to investigation, dipole moment, diffraction, X-rays, and electron gases. So these guys developed these things, and now you can see that the Nobel Prize is now coming more on applying the X-rays. But these guys, and this is a very simplistic cartoon of a powder diffractometer. This is what it comes from. And then in 1917, this person here developed a very important concept on crystal diffractivity, because it's really heavy on mathematics. Mathematics is quite complex, but there's a lot of numbers. The mathematics itself, it's not very complicated, but it's a lot of calculus that has to be done. But he actually described the interaction between the waves with the regular lattice, what we have. So we call this ordered structure a lattice. So he was able to describe this, and then he was developing the theory of this, and then the idea is that he was able to describe a mathematical treatment where diffraction patterns can be mathematically related directly to the individual diffractions. You will learn that later on. And this is called the reciprocal space. That is a rather complex mathematical concept. I will not go into detail in this, but we will use it, and the computer programs are using this all the time. So he developed this kind of a thing in there. And 18, Serre was using X-rays to determine the crystallite size. So now we can apply X-rays, also not having the structure, we can having the crystallite size. So we can say, okay, what is the size of the crystallite? Of course, then it has to be a powder. So this is a powder method. And the idea, it works like this. So this is the powder pattern, and now the half height of this peak corresponds to the crystallite size. So it can be used in material science to look for crystallite sizes. That's the simple idea. And then 21, roughly 10 years later, the previous one, Bragg solved a structure of organic structures. So the organic structure is much more complicated because all the other structures were three-dimensional, like sodium chloride. But now if you have a molecule, the molecule has to organize itself in a regular pattern. And this is much more complicated, of course, because it means that you have to grow the crystal. And these are the first X-ray structures of anthracene and naphthalene for that. And this is actually the result, what you can get from the diffraction image. So these are the electron densities of that. So we don't see that this is carbon or nitrogen. We see just like a small atom. And what we do, we are looking for this kind of a thing and see what is that. But that is the idea. You can see clearly 3 rings here, and there are 2 rings here. But that's not for 100 years ago. And it took months to do this. Now, probably I will show you a video later on, maybe in the final lecture course, where the modern computer programs and diffractometers can make a data collection and solve the structure with an optically pure molecule in 30 seconds or 90 seconds. Because everything is done by the computer. So there are extremely powerful computations between them. And there are some pictures of Weissenberg camera and all the other powder diffractometer and also Weissenberg camera. This is just the idea, development of Weissenberg camera by Weissenberg, and quickly routine made a diffraction experiment because you have to record it. you have to record the diffraction pattern, and this is made by films at that time. That means you have to read the film, and it was really complicated to do this kind of thing. And this is just a principal cartoons and pictures about this. And it looks like this, mechanical instrument, and the film is there, the X-rays are here, they are hitting for the crystal, and then they make this kind of a diffraction pattern. And these diffraction patterns can be then mathematically treated by hand at that time to see where the diffraction is coming from, meaning the crystal. And then the next step here was precision camera, which is in principle modulation of the Weissenberg. And the idea is here that now you get this kind of a thing because this is able to rotate the crystal differently. And we get a diffraction image looking like this. Is like a night sky with stars, but the stars are black and the sky is white. So it's like reverse negative kind of a thing. But now this information here can be converted to the mathematical structures, and this is what we will do, or the computer programs will be doing. And now we will make a big jump. So there is virtually nothing happening for 30, 40 years. Technology. There goes, these are all mechanical instruments, the previous ones. But now in the 70s, the computers were developing, and then robots, meaning moving instruments, which could be programmed by a computer program to do movement. And this is now essence for our business. So if we can give the robot or the instrument to do the measurement by itself, we don't have to do it manually by clicking 1 and 1 and 1 and 1, and then recording that. So in the 70s, we started having the commercial diffractometers. So you can buy an instrument, and the instrument is called diffractometer. Even that in the 70s, it took from 1.5 to 2 years to get an X-ray structure. But then the point is that this, when everything develops, we can get it faster. Still the basics are the same. So everything is the same, only speeding up these things. So that is the idea. So we have here a picture of our instrument from the 70s. This is called the four-circle diffractometer, and that's the crystal is sitting here. You can see it moves like this. And this was a big breakthrough for this. So these are just images of these things. So this is so-called full-circle diffractometer, and this is so-called kappa geometry for this. So it's different geometry, how to control the movement of the crystal. Because what we have to do is still shoot X-rays, and this is a sample holder. It's called the goniometer head. So our sample is here sitting on top of it. So you always consider, okay, what is crystal? You can consider microscopic size, like the size of this crystal, but in real life, it's really tiny. It's so small that we have to work with the microscope. So that was the idea. So in the late 70s, this started coming. In the late 70s, we have these two versions of coming, and the point in there is that we started having detectors. So in here, for example, in this case, here is the detector, and this detector is able to read one reflection at a time. Not more than that. And then this was like, I started my work in the mid-80s. So our instrument, what we had at that time, was from the late 1970s. So it looked like this, the instrument. And it was really tedious work. No computers, no personal computers, nothing like this. You have to do a lot of computer science, or you have to do calculations in a mainframe computer, in a computing center, and so on and so on. It was really tedious kind of a thing. But that's the idea. And then in the 1990s, it's further development. The instruments getting more and more powerful. They were more and more automatic. And one of the big things were there that a new detector type was discovered or taken into use. It's called the area detector. So now it doesn't record one diffraction image at a time. It was recording hundreds. And that's the idea. So that is the idea we call the CCD detectors. And they look like this. So this is actually a picture of our old instrument. We had this big detector, this kind of, it was 15, 16 centimeters in diameter. And then it could be able to record thousands of spots at the same time, or hundreds, let's call it hundreds. And now, further development, more speed, more range for the detectors, and so on and so on. And now we start to see large structures, because prior to 1980s or mid-80s, doing a supramolecular larger structure with more than 100 atoms was no can do. But now, in the late 90s and early 2000, the instruments became so powerful that you can do this kind of a thing and start doing. So that was actually the start of supramolecular crystallography, meaning crystallography of supramolecular structures. And I was lucky in there to follow the development of the instrumentation from these simple ones to more sophisticated ones. And now, even now, there is still development going on, and development is going from the way how we do the X-rays, how we create the X-rays, and how we record them. And now, then this was large supramolecular structure, took maybe 1 or 2 months in the early 2000s. Here it would be, let's say, one day or something like this. Still takes 1 day. At 15 years ago. But then, of course, you know that there is a very powerful system called synchrotron radiation, but these are big facilities. For example, our country doesn't have any. Nordic countries has only one, but for example, England has a few of them. One is the most well-known is our diamond light source that you can have. This is in Grenoble in France, is one, and this is in Barcelona. And the point in there is that you can change the wavelength from microwaves to hard X-rays, so you can tune it. You can do a lot of things with this. But these are extremely expensive to do this. So no normal country even has this. You have to be a rich country in order to have synchrotron. And I've never actually worked on a synchrotron myself. I've used the data from synchrotron, because when you get the data from the synchrotron, it's same as you get the data from your own instrument. So the mathematics and everything is the same. It doesn't matter, but it's extremely powerful thing. And it's so intense that actually it explodes the crystal. So the point is, when you shoot X-rays and singular radiation, in 1 second it will record everything and it explodes the crystal. But the detectors are so fast that they can actually really measure everything, all the information. And that's the idea. But using a synchrotron is a very special case, but it can be done also with powder. This is known thing. So now, this is the pictures of our instruments, what we have. We have 2 instruments. And this is the newest one. So this is called the regard synergy R, which is a rotating anode here. That's the detector. And now, if you look carefully, the detector is curved. And this is a really nice new invention, that you make a curved detector because it speeds up things a lot. And then this is the goniometer. This is the robot that moves. The sample is there, and that's a cooling device. And this is kind of a thing. There are some cooling systems in here, but it's self-containing. And the power, what this is doing, is 1.2 kilowatts, but it's extremely powerful instrument. And this is actually designed and by the company, designed for protein work. So you can do protein crystallography at home with this instrument. We are not doing that protein work. We are using the instrument for a normal work, what we are doing. And then this is the old version of the same instrument, but in here we have 2 radiations. We have a copper and moly radiation. Here is only copper radiation, because the wavelength makes the difference. The wavelength has a meaning for that. But now you can see the detector here and the detector there is the same, because we were able to upgrade on this old instrument. We were able to upgrade the detector. So this instrument became 5 times more powerful only by exchanging the detector. And now the power difference between these two is about 50-fold. So if something takes 50 hours in here, it takes 1 hour in this instrument. So we can easily do 10 structures a day with this instrument without problem. So that is now where we are going and the current. But this is the actual idea. And then what has been done? This is the closing. Soon we'll close the first hour. History of X-ray diffraction. So the achievement, what has been achieved by X-rays? And this also involves a lot of Nobel Prizes for this, because it's a very unique. So in 27, this person here proved the structure of benzene being a planar. So before that, you didn't know that the benzene was planar structure. There were hints and theories about this, but nobody was able to show experimentally. And in experimentally it was done by Catherine Longtate. And here it is. That's the benzene thing. And then in 72 and 32, Robertson solved phthalocyanine. So now we are going already more on the bio-related things, the bigger structures. And then 42, Roy Hodgson solved the structure of collagen and dialite. And then she got the Nobel Prize on X-ray technique of important biochemical substances. So now X-rays are being applied to study something important, biological or whatever. And that is now material science, supramolecular chemistry, biochemistry, medicine, and so on and so on. So it's a technique which is applied to this. But the point is, this time there are no computers, and so all the calculations have to be done by hand. This is what I will show you in the beginning. So this kind of work took years. Very tedious work. 42, this person here, Sumner, got the Nobel Prize demonstrating that proteins can be crystallized. So he got the Nobel Prize on the crystallizing proteins, not for solving the protein structures yet. Because before that, nobody realized that protein can be crystallized. So there's a lot of also learning techniques how to handle the material to become a single crystal. Because of course, what it means that when you say that the proteins are crystallized, they have to be single crystalline. And then in 48, a new journal was created and still exists. It's called Acta Crystallographica, but this is the Lawrence Crystallography Journal. It still exists in there. And then, this is the famous Watson and Crick. They use X-ray diffraction to deduce that the DNA is a double helix. And that is the idea. So X-rays give a huge amount of information on the material what you have, provided that it's crystalline. You have to emphasize this, that if your system is non-crystalline, you will get nothing. And then in 57, vitamin B12 was determined. And then in first globular proteins, there are 62 the Nobel Prize was given to Kendro and Perus for the studies of globular proteins. That was and this is 60 years ago. And then the idea is surprising that the development was really fast, because this was related to the crystallizing of this material. And now still there is hundreds of thousands of protein structures only, not millions. And that is the point. So because the more complex they go, the more difficult it is to crystallize them. And Bragg solved the lysozyme, the bigger one, and then 82, Aaron Black got the electron microscopy crystallographic work on that, so you can use also electron diffraction for this. And then in 85, actually I was in the crystallographic meeting when this Nobel Prize was launched by Hartmann and Karl, about a mathematical treatment, how to solve a structure. And you will do it and learn it also during this course, how to do this. But the mathematics, how to do this, was developed and put into a computer program by these two guys. So they developed the mathematics, how to do this. And now we don't have to worry about the mathematics anymore. It works very well. That's the idea. And it's only about 40 years ago when this was done. And this also relates to the development of computers. And this direct methods, this is the idea for the outstanding direct methods. The direct methods now is the phase problem. Remember from the beginning, I told you that when we have a wave, we know the amplitude and the wavelength. But the thing we don't know, which is impossible to measure in a certain sense, is the wave, the phase of this. So where is the minima and maxima for it? Because it can change. It can be different from different waves. And in order to do this, we have to know the phase. in principle, you can consider the phase as a number. So we have to know if the number is 90 or 95 or 110 or so. We have to know it, because without this, the mathematics don't work. And these guys, when we're doing this, they managed to create a mathematical treatment on the diffraction data. So the data knows this. So data contains information about this, but you cannot see directly. So they developed a mathematical treatment how to do this, and now this is embedded in all the existing programs, and they are really powerful. So you actually don't realize what is happening inside there. There is a lot of happening in there. But this is the idea of how it was developed, and it's only 40 years old. And now if you would have a very slow computer, it'll take a long time to do this, but nowadays the computers are so powerful that this thing takes a second or two. So the mathematical treatment of these things. And then they are so powerful because what these direct methods are doing, they will give a guess of the phase. They are trying to figure out what is the phase of this reflection and diffracted beam. And then when you have it, they will give the number and then see what happened. Because later on in the course, you'll realize why it's needed for the mathematics. And now I think that is my final slide in this introduction, just to go on in there. What is now the state of the art, more or less? So what you can do with, so you can get 100,000 or more atoms in there. And now what is there? You can see resolution. You will learn later on what is the resolution. But the resolution here, 2.4 angstroms, it actually sees the amino acids. It doesn't see the individual atoms. But later on in the course, you will learn where does this resolution come from. But the point in there is that it's 25 nanometers in diameter. So these are absolutely outstandingly huge systems. And before that, let's say 15 years ago or so, it was considered impossible. But now you can even crystallize a virus, and you can get the extra structure of a virus. And this is, of course, huge impact for medicine and also studies of this, what is happening in there. But that's the idea. And this is actually how the protein looks like when you're showing the surface of the protein. Because, of course, the atoms are not balls, how we normally show them. Ball and stick model is not the real one. They are more like spheres joined together, and then you create the surface of this kind. And then, for example, drug molecule might go in this hole here and have an impact on what is happening. So this is the information what we can get out. And I think that was my final slide for this. And now if you have any questions, so now it's 1 o'clock already. If you have any questions concerning this, you can ask now. We have a short break now for 5-10 minutes. What is the normal thing? 5 minutes is fine. Okay. Yes, for this handouts. So you don't have to, you can make notes, and of course you can do. But the point in there, I will then provide you, if there's an email address for all of you, then I will be able to provide you the PDFs for all of these. They're quite big, some of them, but I will manage how to do it. Okay, now then is the 5-minute break. You will learn it later on, because the point in there is that how the diffraction, okay, we are now going, this will be explained later, but anyway, you can consider that diffraction happens from a plane, remember this kind of a thing, like a mirror. The mathematical treatment, the reciprocal rate, transforms the plane into a point. And this point is actually what we are measuring. So later on you will see a diffraction pattern, and the diffraction pattern is actually the reciprocal presentation of the orientation of information inside a crystal. But we are too early to give the answer because you will learn it later on where this comes from. Okay? Any other?
Sir, one more question.
Yes.
Why the synchrotrons you have mentioned?
Yeah.
The synchrotrons, how they create the more high-speed X-rays?
Yeah, because the point in there that what is happening here, they circulate the values. This is the synchrotron, and then These are hitting with a very high speed to an anode. You will see that next lecture will be about X-rays, how they are made. And it comes from the speed of the electron when it hits the anode, and that makes the power. So that's the idea. So that's why they are 1 kilometer in size. And
The
then
speed also gives them more.
yes, that's the momentum what is there. So that is the actual idea why it's so powerful. So brightness is about 1 million times more than we normally have.
Okay, sir.
Okay?
Thank you.
Okay, now the 5-minute break.